So there was a question about negative magnifications, and I'll move to the slides for that for a second. Escape. So yesterday at the end of the lecture, when time was getting tight, I mentioned that we might have negative magnifications. And this doesn't mean that suddenly your intensity of light gets negative and you somehow go from emission to absorption. What this means is there is a flipping of an image, and I'll try to explain it here. Hopefully the writing is large enough for you to see. So we have a magnification, which is basically a ratio of, if you have a solid angle down here in the source plane, and then you form an image over here, which is presumably larger. It's just the ratio of an angle subtended here and an angle over here. But what you need to remember, and what gets often overlooked by me and also in the texts that are in the reading lists, is that theta and beta are not scalars, they are vectors. And so when you would consider, so you should actually consider them, let's say, for a circular symmetric lens in cylindrical coordinates. So each of these vectors is basically has a component in the radial direction, in this direction, and also in the tangential direction. So now I'll just briefly consider a type of an image where you can see this. Let's take something like this. So this is a source that has a clear asymmetry both in this direction, in the tangential direction, it's pointing that way, but also in the radial direction, because in the radial direction it's pointing this way. And I'll just take these 3 points that form the vertices of this. So if you would take this point and you lens it, for a point mass lens, let's say, you'll get one image over here, far from the lens, and another image close to the lens. Then you do the same for this image, for this vertex, whatever. For this point, you get an image here, and on the inside, and another image on the outside. And then you consider this last point. So you get an outer image somewhere over here, because you add the Einstein radius to it, to the first order, and a second image will be formed over here. Am I doing this right? No, the second image will be formed over here. Okay, I got confused myself. So the separation between the two images is roughly 2 Einstein radii always. And so when I try to, okay, this, well, okay. So for the big image, it's probably clear what is happening. That's just a much bigger version of this triangle. So this triangle, I'm not very good at drawing angles, but this triangle is just a large version of this triangle. So you would consider, again, this in the cylindrical coordinates. In the radial direction, the vector is the same. It's pointing in this direction. It just got bigger, so that's positive. And that's in the tangential direction. The vectors are the same, just larger, so positive. In the radial direction, they point in the same direction, just got bigger, that's positive. So this means this theta over beta and d phi over d d beta is overly positive for the outside image. What happens down here is a bit more, I didn't draw it very well, so I'll just label the points again. So this is A, this would be B prime, and this is C and C prime. And now we see that A, yes. So now in the radial direction, when you consider where does, for example, the B prime to C prime vector and a B to C, they have the same pointing, right? Like this. They're just scaled by some value, so this is still positive. But B to A and B prime to A prime are reversed. So how to draw this? So when you do vector, let's say A, B minus A over B prime minus C prime, they are proportional to some scaling, which is the magnification, but their directions are reversed. Here, this is positive, this is negative, so you get negative sign on the magnification. But it doesn't mean that your image got negative. It just means that the vector that used to be like this in the tangential direction gets reversed to this. So if you increase this vector, you also increase the magnitude of this vector, but you just make it more negative. I hope that's sort of answer to the question. What matters when you consider the brightness of the images is not the direction of the vector, just its magnitude, because if you would take the ratio of the areas now, you don't care what is the sign. You just know that this image is much larger than this image, so the ratio of areas is huge, and here it's maybe closer to unity for what I draw. Is that okay? Good. If not, then I'll try to come up with a better argument in the afternoon. Okay. So again, welcome to the class today. I'm happy we have quite a few people still on board. Today I'll pick up from where we were yesterday. So I'll talk first about the point mass lenses, and now no more theory of point mass lenses. We'll just look at the applications. And the application will be microlensing, which I will spend a few slides on. And then, as someone who works on galaxies, I'll move to the most theoretical part of this course. It's only going to get better from there. And we will move from these point mass lenses, which are good approximation for maybe a star or a planet or a black hole, to what I call realistic lenses, which means something that behaves like a galaxy. I'll just briefly reiterate what we did yesterday. We introduced deflection angle. We talked about lensing equation. We defined Einstein radius, which is the distance between the center of the lens and an image, the characteristic distance. We talked about a point mass lens and how it always has two images, unless our approximations we are putting into the calculations fall apart. We talked about magnification and that it can be positive and negative, but we won't really care about it too much in this course. Just a brief flashpoint. These are some slides from yesterday, so if you have access to the internet, you can go back to them. This is the deflection angle that we defined. This is the lensing equation, which relates the position in the source plane. Or if you have an image in the sky, you can basically use the mapping for the deflection angle to find where your source originally was. Einstein radius, it's depending only on the mass of the lens and some distances to the lens and to the source. And And that was pretty much the summary of the theory. But just to make sure that we have some concepts on board, I would like you to go to kahoot.it and we will run a short game again. So what we will do now, we'll just briefly run through some of the questions from yesterday. Short time to put in your answers, but the point is just not to test you necessarily, but just to have a look at, to remind you of some concepts we covered yesterday. Are we still waiting for people? I assume yes. Or no? Anyone still connecting? Very good. I'll wait. Also today, I'll try not to close this multiple times. So we should be able to stay logged in together. So this is a problem we saw yesterday. You have a lens that looks like this. It has these 5 mass elements, all of the same mass. And the question is, which direction are these 3 rays of light going to bend? Very well. Okay. Good. Then we do next. So now there's the modified version of this, where we extended the mass sheet to infinity. So now your lens has the uniform surface density and goes all the way from infinity to infinity. Very well. So this is completely symmetric situation. For each ray, it is the same mass in all directions. There is no bending included. And this should be the last one of this part. So these are the rabbits we saw yesterday, and a bit of related to what I was showing before. So if you have a lens and you see some extended images, which configuration is the possible one given the orientation of the rabbits? Very good. So the point is that the rabbits are flipped in the tangential direction, but not in the radial one. And with that, I'll go back to the slides. So we talked about point mass lenses a lot yesterday, and today I'll just give a brief overview. What is this good for? Because that seems like galaxies are not point-like. Why did we do this? But the fact is there is a lot of stuff that behaves like a point-like lens, and these are stars and planets and black holes, indeed. So the nice thing about these objects is that they are circularly symmetric to high accuracy. They are non-transparent. There is no ray that can go directly through a star, so you avoid the singularity in the middle. There is many of stars in the galaxy and also outside. So the microlensing would basically happen when you have, let's say, a star passing in front of another star and doing the lensing that, as we saw yesterday with the sun. The problem is that the typical angular separation of this is very small. You can't resolve it even with the best telescopes. But what you can see if I just skip this. So these were you can't resolve the individual images, but what you can resolve is the total magnification of the 2 images that will form for a point mass lens. And so imagine you have a background star, there is a foreground star moving in front of it. As you are far away, the background star has the same brightness, but then as your lens moves above the star, the lensing kicks in. Then if they are perfectly aligned, this shoots up to infinity, and then the total flux goes down again. And normally lensing events are stationary for galaxies, but stars have some pretty decent velocities. So you can actually see these happening in real time on a timescales of days to years. And so the infinity happens when you have a perfect alignment at some point that the background star is aligned perfectly with the foreground star. But lensing also works if the alignment is never perfect. And so this is the same figure but now showing different offsets or different closest approaches between the background star and the foreground star. Here is offset by the closest approach by 0.1 Einstein radius, and you see the same curve but not going to infinity anymore. And as the closest approach gets further and further away, this effect gets smaller and smaller. At some point, there is basically nothing because the lensing is minimum. So this has been done with stars, but what is very exciting prospect of this is that planets are also gravitational lenses. And so if you can see, okay, you can't see that very well, but imagine you have a star passing in front of a background star, and so your curve will look something like this, as we saw in the previous slide. Now, if that star has a small planet orbiting it, that is basically having two lenses moving in front of the foreground star. So first you have the big kick from the central star, which has a large Einstein radius, large magnification. But then at some point the planet will also act as a lens, and you will see this blip here, seen here as well. So basically you go up, the big star, the foreground star is doing most of the lensing, then it moves away, then the planet kicks in, then it goes down, and you can see roughly how this would look like for a telescope over here. So there's the first lensing event when the star does the lensing. There's a second lensing event where the planet does the lensing. This can get much more complicated when you add more planets, when you add the fact that also our sun moves. But this is basically the principle. And the nice thing is that when you consider how we are detecting planets, we are looking for Doppler shifts, maybe, that the mass of the star is tugging on the central, mass of the planet is tugging on the central star, but this works for very massive planets. Then you have transits, but then you have to be really lucky that you have a planet that is making a large enough dip when it's transiting in front of a star. This doesn't rely on having, and you have to have a pretty bright host star to have. This only depends on the background star, not on the host star. So this is a very powerful technique for, let's say, finding planets around less massive stars and also at large distances. And people are trying to use this actively for over 20 years. The two big programs right now is OGO and MOA, run by Poland and run by Japanese and New Zealand team. With pretty small telescopes, because what you don't need high resolution here. What you need to do is to monitor a lot of stars very frequently and hoping there will be microlensing events. And sure, most of the time what you will find is variable stars. Loads of variable stars. But none of the variable stars can make this curve under most conditions. And so just to show you how this works, so this is a map from the OGO survey. Okay, you can't really see, there are some shaded areas over here, so they're looking towards the galactic bulge. The advantage of this line of sight is there's a lot of stars that can act as a background source. They're looking at the disk as well, and LMC and SMC, so basically you want to have large density of sources. They do it super frequently, so this is a zoom in on the galactic bulge. For the free red fields, they take a snapshot every 19 minutes. And then it gets lower. The cyan part is once every 2 days. Of course, weather permitting, but. And so this is weather permitting, but there have been also studies done with Spitzer, which has been also used for microlensing studies. And now Gaia, which is doing this massive all-sky survey with scanning the sky over and over again, is also going to be a pretty good microlensing tool. And indeed, the first microlensing event from Gaia was detected in September. In terms of total number of planets detected, microlensing isn't this great. So this is, I took this from NASA website a few days ago. They have this archive of all the exoplanets ever detected. And so microlensing is this purple thing that you kind of starts kicking in around 2005, 2006, and it's actually very few planets, even up to this day. But they are a bit of special planets, because what you can do with them, you don't have to have a close approach to the star or a very massive planet to kick in the Doppler shift or the transit. So they are in this interesting regime where the planet has relatively low mass, but is also pretty far from its host star. And just to give an example of a recent, well, not so recent discovery, is there's an interesting image of this planet or exoplanet. This was found in 2017 by the Algol survey, and then later this was refined. But what they found, it is at the mass of about 1.4 Earths. It's orbiting around, I think, an M-dwarf star, so it's super icy and very cold. But the point is how far away it is from us. It's 4 kiloparsecs away, and this is a powerful thing about microlensing. With transits or Doppler shifts, you're limited to relatively nearby stars. With microlensing, you can go far. And that's it for microlensing. Questions now? If not, I'll then move to the theory part. So this was all about point-like lenses. And I promised you yesterday that we will try to explain RxJ1131, this nice lens with 4 images, Einstein ring, time delay, subtraction in the lens throughout this course. And there was this question already yesterday, how come we have 3 images here and 1 image here? And so far with the point-like lenses, you can always form only 2 images. So how did this happen? And indeed, and the point is, well, galaxies are not point-like, as you can assume. So today I'll cover a few additional topics. I'll talk about that basically galaxies are not point-like, so they have some density profile. I'll talk about some density profile that's been pretty useful for easy calculations and actually works pretty well in real life. I'll introduce lensing potential. I'll talk a bit about convergence. I'll try to talk a bit more about magnifications. I'll introduce caustics and critical curves, which you will often see in lensing papers. And I'll talk about time delay surface, which is actually the best way how to solve complicated lenses. Again, I'll just stress this is the most theoretical part of the course. From today onwards, we get more towards new results and looking at how we actually do science. So again, as you have seen this plot before, and everyone should have a leaflet by now, this is the typical lensing configuration we are encountering. You have the angles labeled. Here is the observer. Here is your lens. Here is the source, maybe offset from the lens. There are these 3 characteristic distances from the observer to the lens, from the lens to the source, from observer to the source, and it is not necessarily the case that DLS and DL equals DS. Definitely not for high redshift sources. And if you are still logged into Kahoot, I would like you to go there. And we will do the next question. So, a wild guess. Take these 2 galaxies. So this is Andromeda. This is just some elliptical lens I found. Elliptical galaxy I found. Which one of them do you think will be a better lens? Which one is more likely to produce Einstein arcs or actually act as a lens in general? Nice. So the elliptical one, and indeed that's the correct answer. So to have multiple images or to act as a good strong lens, you want to have as massive galaxy as you can get. And ellipticals are typically much more massive than spiral galaxies, and definitely much more massive than Andromeda. And that also gives an advantage for us, because for a lot of lenses, they're just elliptical galaxies. They don't have massive disks or complicated structure. ellipticals are reasonably easy to handle. Okay, so the problem we are having today is that the galaxies are not point masses, but because a lot of lenses might be elliptical, they are not necessarily too complicated either. And an even better thing that we have to think about is that actually most of their mass is in the dark matter halo, which is very smooth often. So what we need to address this problem, how do realistic galaxies work as lenses, we need to have some ideally analytic profile for their density distribution. Later we can add some irregularities to that, it will be that 5, and maybe account for nearby galaxies, because often galaxies come in groups or they need small galaxies around. And the nice thing is that we spent the better part of the 20th century creating analytic profiles for galaxies and stars and the dark matter in them. There is the number of Frank-White, there is Einasto, there is a Plummer profile, if you know it. There is a Cersig in 2D. And as we saw yesterday, lensing is that essentially ideally you want to collapse your lens into a 2D object because the depth doesn't matter that much. So what you try to do normally is to do this all in 2D projections, unless you really like 3-dimensional integrals. And you want something that's simple but decently flexible. And we have something like that, and it's called the singular isothermal sphere. So this assumes a very basic thing. It assumes that the matter in the galaxy is dynamically relaxed. So it's sort of in the same temperature, if you would say. And if it's at the same temperature, then the thermal pressure inside the galaxy balances the gravity. And if you would do the equations, and there is a nice derivation in Narayan and Bartolomon paper on the reading list, what you get is basically from the thermal equilibrium is that your density goes in 1 over r squared, where sigma square is the velocity dispersion in your galaxy, which is constant everywhere because your temperature goes as kT equals 1 is proportional to the velocity dispersion. And then when you integrate this, your mass enclosed just goes as sigma square, which is constant for the galaxy, times radius. There's also, you can make this into something more involved when it's a single isothermal ellipsoid, because not the galaxies are not spheres, and we'll see that later. But this approach is often sufficient. And again, because most of the lensing is done, often the lenses are elliptical galaxies with smooth dark matter halos, or also often our observational constraints are not necessarily good enough to distinguish between this and more complicated models. There is a major shortcoming of this model that we often need to ignore. So when you look at the mass of the galaxy, it's proportional to the radius. And you might see where the problem is going to come from. So if you look at your radius, here is the mass within that radius, which is proportional to the radius. It goes like this to infinity, as you put the radius to infinity. But what actually, so this is not the best thing ever, but lensing often happens at pretty small angular separations, and we saw that yesterday, and we'll see that again, maybe on a scales of few kiloparsecs, where this approximation works very well. And then what happens outwards as you go to the virial radius, and there will be some truncation. What people mostly do is that they just impose your galaxy stops physically at some point. It doesn't extend all the way to infinity, which seems to be a pretty reasonable assumption, as galaxies typically have edges. Okay, so I'll try to show a lot of equations now, but I'll talk you through them. So what we saw yesterday was the yesterday we derived the Einstein's result, which is basically the deflection angle is at some, for a circular symmetric case now. The deflection angle is basically just proportional to the deflection angle at a, okay. So I don't confuse you too much. If you take your handout, I forgot my big one. If you take the handouts and you look at the vector x, which tells you how far your image is from the center of the lens, the deflection angle at that position is only proportional to the mass enclosed over 1 over x, and this term over here only defines the direction, that if your x is positive, the deflection angle goes up, down. No, if the angle is positive, your deflection angle goes up. If you are on the bottom part of the lens, you basically push the image away from the lens. To illustrate what I mean in these complicated words, here is the observer, source, here is your lens. Here is the actual path that the ray takes. Here is your deflection angle. So if your x prime, so if your x vector is pointing upwards, your alpha is also going to be up. If you reverse this, then your alpha is pointing downwards. That's all that is. But basically what this means is, for deflection angle, we only care about the mass enclosed within this radius. So we can integrate this using the surface density, and we get something very nice, which is 4 pi sigma square over c square. Again, sigma is the velocity dispersion of the lens, and again, this vector component to make sure we are pointing in the right direction, either up or down. The vector components here look annoying, but they will be actually important as we go later on. And then we have the reduced deflection angle that enters the lensing equation. And this is just alpha hat scaled by the two distances. So you just multiply this through. And then we saw yesterday that the basic lensing equation is beta theta equals theta minus alpha theta. And you can basically substitute this here, where I took the liberty of replacing x with theta. And the simple reason for that is that in the small angle approximation, x vector equals theta vector times dl. This is my theta, this is my dl, and this gives me this scale. So what we are left with is actually a pretty simple lensing equation. Theta comes in here. This term over here only depends on the direction of theta. So whether if theta is positive, this term stays negative. If theta is negative, then this term becomes positive. And then you get the source position. So that's actually pretty handy. And I would, so what we can do, the first thing is make this even simpler and put the source directly behind the lens. This is what we did yesterday, where we derived the Einstein radius. And actually, this is exactly what we are going to do now. So we consider the limiting case where beta equals 0. You take this equation. This is 0. And then basically you have, theta has to be equal to this term, whether it's positive or negative. And as we saw yesterday, if you remember, for this perfectly aligned lens, you will get a nice ring with the Einstein with the radius of which we call Einstein radius, and that's exactly this quantity here. And what that means in principle is now for source perfectly behind the lens, you basically form one image at Einstein radius, one image at minus Einstein radius, but because of the circular symmetry, this actually you can rotate this by any angle, and you form this very nice ring in the sky with the radius called Einstein radius. Okay, so we found the Einstein radius. So very handily, it's just this term over here. So we can rewrite the lensing equation again, and now this is again back to the general form. And now beta of theta equals theta minus Einstein radius and direction of theta. And so this is actually looks almost too simple. It is solving this is actually a bit more tricky because it depends on where exactly your beta is. And I'll skip. For this lecture, I decided to skip the detailed derivation, but I can do it later. But I'll just basically explain that there are three defining regimes. So if you think that if beta is much larger than Einstein radius, then if beta is equal to Einstein radius, if Einstein radius here equals theta minus Einstein radius modulo theta, and if beta is smaller than the Einstein radius. And how this looks, in fact, is this. So first consider beta is larger than Einstein radius. So here is your lens. Here is the Einstein radius, which is properly defined in the sky, but we also can draw the same distance in the source plane. Here is the center of the lens. Here is the ring with Einstein radius. Here is your source. And so the solution here for this regime is that that was supposed to be theta. My deepest apologies. So the solution is that theta, the position of your image, is just the beta vector. So this is beta. You have beta here plus Einstein radius, and that means you basically have here at the Einstein radius on top of that, you have a single image over here, far from the lens. And you see already there's a big difference compared to the point mass lens, where with the point mass lenses, we have always two images. When we did the math, we never had a single image. So, and this is in a way allows us to have a configuration where we have only a single image. If you are very far from the lens, which is neat. Then what happens where beta equals Einstein radius, or I said around Einstein radius, then basically this solution holds as well. So this should be theta equals beta plus Einstein radius. But now you also allow the negative solution. There are two solutions for the equation. And so if you are exactly the Einstein radius, one image will be formed at Einstein radius plus Einstein radius, which is 2 Einstein radii, so just over here. And there is also another image which is formed at Einstein radius minus Einstein radius, which is very close to the center of the lens. So now we see as the source moves closer to the lens and gets to the distance of 1 Einstein radius, suddenly move from having one image to having two images. And then the final configuration is where your source moves inside this Einstein radius ring. And now actually not much changes. Basically, you swap from this type of solution to this type of solution. Again, this should be theta equals beta plus minus Einstein radius. except now as you go more towards the center, the distance here gets shorter, so this image moves more and more inwards, and this image moves more and more outwards. And then, of course, there is the final solution that we just discussed, which is what happens if beta equals 0. And as you can expect, then the source is completely in the center, and you form a nice Einstein ring with a radius of 1 Einstein radius. I know this is a bit rushed. Question to the audience: would you like me to do the derivation of this on the board? Very good. Blah, blah. So I'll have a word of warning here. So this configuration, if you go to the reading list, which again is not compulsory, so it's discussed in the Narayan and Bartolman paper, but also in the Meneghetti paper. And in the Narayan and Bartolman paper, this is basically, they don't provide the full derivation, and also in the previous terms, they drop the vector nature of the angle. So it's very difficult to follow. Meneghetti paper has a full derivation, has a much better derivation of this. So let me just start from the point where we had, which is the beta vector, and careful, this is a vector now, equals theta minus Einstein radius times theta vector over magnitude of theta. And just for you to understand what is happening here, again, if you have a source, here you have the observer. What this means, if you have some angle theta pointing outwards, the angle beta down here is basically theta, or the vector here is basically going to, the angle here is basically going to be theta minus Einstein minus the angle corresponding to the Einstein radius. And if your theta is negative, so now this is negative, theta, this thing over here, theta over minus, basically becomes positive because here you have negative thing, this is a positive thing minus sign. So your correction by the Einstein radius is pointing upwards. It's just a symmetrically, just a symmetric situation. And now comes the hard part. So what you need to realize again is that the sign of this, if theta is greater than 0, is positive, and vice versa. So if it's less than 0, it's negative. And so now, let's start with something simple. Let's say that beta equals Einstein radius. So we have our angle beta pointing upwards. The magnitude is 1 Einstein radius. So then what you get in this equation, you have Einstein radius pointing upwards equals theta, which is what we are trying to solve for, minus magnitude of the Einstein radius plus theta over absolute value of theta. And now, if theta was completely positive, so if you consider that theta is greater than 0, then what you get from this is just Einstein radius equals theta minus this is plus, plus, goes to 1, minus Einstein radius. And what comes out of this is 2 Einstein radii equals theta pointing upwards. I'll try to separate this visually. So if this is positive, this part, this becomes 1, except you keep the direction, which is pointing upwards. So you basically add your beta plus another Einstein radius on that, and here we said that beta equals Einstein radius. And you can consider another option where theta is smaller than 0. That can also happen. That means we are looking down below the axis of symmetry, and then you get, again, beta equals Einstein radius, and that is equal to theta, and now we swap the sign. Because this will be negative, this is always positive, so this becomes minus 1. Minus 1 times minus 1 is plus theta epsilon. And this looks deceptively like we have a solution here, right? This thing is the same, this thing is the same, and therefore theta equals 0. Right? You can subtract this from this, and you get this. And so we derived just this limiting configuration, where for beta, at 1 Einstein radius, we have one image at 2 Einstein radii, the other image at 0. For consistency, there should be, equals somewhere here, but you get that. Then we can do the other extreme, the one on the very left, where your beta is greater than Einstein radius. So I'll set beta equals Einstein radius plus some epsilon thing that you might know from algebra. So this is some vector that is going to be positive. And that is equal to theta minus Einstein radius, theta over. So we use exactly the same approach as we did here. Consider positive theta, negative theta, and see what solutions we get. So if theta is greater than 0, then what we get is, on one hand, we have theta epsilon, theta e plus epsilon equals theta minus theta epsilon. And from this means that theta equals 2 Einstein radii plus whatever vector epsilon we put here. And this is positive, so this is always greater than 0, right? We are still consistent. We set theta is greater than 0, this is greater than 0. We have a solution, and it's the solution we see here, that you have basically an image at position of the source plus another Einstein radius somewhere over here. So now we need to lose the negative solution, and that happens through this. So you have theta, and you said it's smaller than 0. It's the second limiting case. It's the second option we have. And then you have, on one hand, you have theta Einstein plus epsilon equals theta plus theta epsilon, because the sign here gets reversed. And then, of course, we can totally solve this, right? Subtract theta epsilon from here, and you get theta equals epsilon. We took this. This is what we start with. Theta is negative, so the sign here gets reversed to plus. So this is what we, by definition, our left-hand side is. This is our right-hand side with the sign flipped, theta equals epsilon, and we go ooh, because by definition here, epsilon was greater than 0, but we said theta is going to be smaller than 0. I should make it vector. There is no solution here that is consistent. If you say that theta has to be less than 0, so you can flip the sign here, you get that the only solution that would be allowed is a positive one, which doesn't work. We said it's going to be negative. This is the only solution that in that case would mean it's positive, so this is not consistent. And we drop the solution. We said theta was going to be negative. It has to be, if it's negative, we get a result that it has to be positive. There is no central image here. And then you can repeat the exercise the last time and make epsilon is greater than, is a smaller than 0 vector, which means it's negative now. And how will this pan out? This part over here is not going to change. So we have 2 Einstein radii plus epsilon. Now epsilon got somewhat negative. That doesn't matter. This is still going to be positive because our beta is positive. It's this plus some additional vector. But now this solution that I crossed out holds. We said epsilon is negative, and for a solution where we say that theta is negative, we actually get that theta is equal to some negative quantity, and that is this image over here. What I'll do, I'll send you a full derivation. I'll send you this proof again, so you can go over it. But basically what it adds up to, we consider the free limiting cases we have here, which is that beta, what happens with beta is larger than Einstein radius. And then we found there is only a positive solution possible. If beta is smaller than the Einstein radius, we found that there are 2 solutions, the one over here and down over here, which is the negative one. And finally, we found that if we set beta equals to Einstein radius, that's the bordering case where one image forms at 2 Einstein radii and the other one forms at 0. I'll let you. Okay, I think there are questions because there was a lot of. What I wanted to say by this that this singular isothermal sphere profile, unlike point mass, has basically two different options. You either have one image, or you have 2 images, or if you have perfect alignment, you'll get the Einstein ring. But there is this limiting case where we go from one image to 2 images over there, and I would like to highlight that because that is a special name. So this is we call this line where we go from one image to 2 images, in this case, the critical line. And the corresponding positions of the source in the source plane are called caustics, which is where the behavior of your lens and image configuration changes. You go from having one image on the outside to suddenly second image appearing close to your lens. So we can get 1 or 2 images now, which is better than having always 2 images that we had yesterday. Yet we are still having this lens with 4 images that we don't know how to produce. And the problem is that a single isothermal sphere can't explain the 4 images at all. And the problem is that single isothermal sphere is maybe too ideal of a potential. And this is a quote from a SASFI lectures that you have access to from Chris Kochanek, which is quite famous in the field because he's using caps lock in a textbook twice. And it is basically that when you are actually modeling actual gravitational lenses, you can never, and really never, neglect the fact that there is some angular structure to your potential, which means the circular symmetry that we assumed in the singular isothermal profile doesn't help for real galaxies. There is always something happening that makes the galaxy not to be spherically symmetric. What a surprise. And this is also very hard to solve by hand because when you have elliptical mass distribution, suddenly projecting into 2D, which we could do with a single isothermal sphere, is difficult, often has to be done numerically. And the real galaxies are even worse than that. So even an elliptical galaxy is not only elliptical in 2D, it's elliptical in 3D. It has some 3D triaxiality, which I'll completely ignore for the rest of the course and most of my career, because that's a bit too much. So if you would allow me to skip some. So the approach we had over here, blah, 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 which is basically solving the lensing equation by hand, is not going to work very well when we start putting in elliptical potentials. So now we moved from point mass to spherically, to isothermal sphere. Now we need to make this elliptical. And this is going to be very difficult to solve unless you take really hideous functions as normal solutions. So if I forward here, there is a way how to get out of this. It's numerical, but we can do that. And I would like to talk about potentials for a moment. So we know potentials from gravity very well. So just go back to your mechanics course, and you know that if you have some density distribution in a space of mass, if you have some density distribution, your gravitational potential at a given point, you can calculate that. And that tells you, how much force is each of these density elements going to contribute. And the nice thing about potential is when you take the gradient of it at a given point, it gives you the force at that point. I'm somewhere in the world. If I measured my potential here and I took a gradient of that, I know it's going to be pointing downwards. I can do it in the universe where I have much more complicated mass distribution than having one Earth to sit on. And also another nice thing about potential is that for those of you who did the higher analysis, it's that when you take the Poisson equation, when you take the second derivatives of it, you recover the density distribution, which is just the nature of your potential is a multidimensional integral over your density distribution. So if you differentiate it enough, then you get the underlying local density. So this has some very nice properties, right? It's proportional to the mass distribution. If you differentiate this, you get force. And the trick we'll use now, we can try to do something like this, but in 2D. So let's take your three-dimensional gravitational potential over here and just integrate it along the line of sight. And we'll call this now the lensing or the effective potential. There are some prefactors here, so the equations work out in nice units. But basically the point here is okay, I lost the, oh, there we go. The point is when you would consider, let's say, having a point like mass, having not even a point like mass, if you draw your potential, the gravitational potential is line of sight. There is some massive object over here, so the potential goes down, then climbs up again as you move away from it. Your lensing potential is basically just integrate all of this along the line of sight. So in this case, it's basically going to be the area under this curve, modulo the distance element. And then there are two handy properties, because if you put these prefactors in, the gradient of the lensing potential gives you the deflection angle. And this is not very surprising. Because basically what this will give you, this is some sort of mass enclosed within the radius, and this is your deflection angle. And then if you put this into the lensing equation, you have your source position equals your image position minus the gradient of this new potential at that position. And as you will see, I'm not very consistent whether I'm saying small psi or capital psi, so my apologies. And then if I push this a bit further, here, when we did the second derivative of potential, we recovered the volume density. Well, this is just the surface. This is basically 2D integral of your potential, which is proportional to density. So the Poisson's equation now gives you some sort of surface density. And there is some prefactor here because we put some prefactors over here. I'll just let you stare through this for a moment. It's not the most intuitive way how to approach the complex problems we'll try to explore in the next 40 minutes. But all this does is say, my mass distribution is now going to be very complex. In real life, when you do gravitational physics, having complex mass distribution can be often dealt with effectively by using potential. You don't have to calculate force from each element. If you know what your potential is, you can get the force at every point. So now we are trying to say, okay, lensing is sensitive not to the 3D mass distribution, but to the 2D mass distribution. So let's try to do the very similar thing, where we try to get the deflection angle based on the 2D mass distribution, but not by direct calculation, but by having some nice function, some potential that we can simply differentiate. And again, the advantage of this approach is that we now can do, in principle, much more complex mass distribution as long as we have an expression for the potential for it. Okay. I'll try to, I know this is a lot, so I'll try to bring up the Kahoot again. If you would connect, and I'll fire 2 quick questions for you guys. Okay, so the quiz question we were supposed to be saying is consider this lensing potential equation, and I'll try to do this now by the show of hands. So, and a spherically symmetric line. So you can think of a point mass of the single isothermal sphere we were dealing with earlier today. So in general case for this type of lens, will the lensing potential how will it behave? Is it going to be always negative? And if yes, will it decrease towards the center of the lens? Is it going to be always negative but increase towards the center of the lens? Is it going to be always positive but go down towards the center of the lens? Or is it going to be always positive and actually go up towards the center of the lens? Just to stress out, just to make it clear, all these prefactors are real and positive. Okay, I'll do a show of hands. Who thinks it's going to be negative and decrease towards the center of the lens? Anyone who thinks it's going to be always, okay, good. Always negative and increase towards the center of the lens? Okay, 2 people. Positive and go down towards the center of the lens? Good. And positive and go up towards the center of the lens? Good. Okay. I think you can find the answer in this sketch. So here is your potential, the gravitational potential, and we know from the definition of it, if there is a positive mass here, which there always is, it's negative. It's 0 at infinity, negative, and gets more negative the closer you go to the center of the mass. So the area under this curve is going to be always negative. What you just do is basically sum up all these negative elements. Yes, you do modulo of this direction, but the total area under this curve is negative. Why area is negative? Because you are measuring it from the 0 point over here. So if we were doing something like this, that would be positive, but what we are doing is the negative thing. If you remember how it works for a point, for a single mass, there is a negative sign over here. So if you integrate this, which is a negative thing, you'll end up having something very negative because it's symmetric also. And what happens, so if you consider your lens, here is the center of it. So you have 2 potential options. If you go on the outside of the lens, and you go on the inside of the lens, good point. Let's take a point mass lens. So over here, the mass is always the same because the mass is in the center, but here the 1 over r term is smaller than 1 over here. And what this means that the potential, if you over here, is smaller than the potential over here. So as you would go closer to the center of the lens, the depth of this curve gets higher and higher. So instead of having something like this, you have something much deeper. And that means that the total area under the curve got more negative. So we are in the option A. The lensing potential is going to be negative, and it will actually decrease towards the center of a point mass lens. And that is actually very handy. I'll sacrifice now this part of the derivation. So take the lens from the outside. So your potential goes down as you go to the center of the lens. So this is your lensing potential. But also your gravitational potential goes down as you go to the center of the lens. And if you consider the equation we had over here, let's start. Hang on. Oh yeah, this one. The gradient gives you the deflection angle. So if you are somewhere over here, The gradient, so if you take the local derivative of this is increasing with the radius, right? It's very negative over here. As you increase the radius, this potential increases, so the gradient is going to be positive. And that means this angle is going to point away from the lens. And this is what we saw before, that if you have an image if you have a source behind the lens, the deflection angle is pushing it away from the lens. Not closer, away from the lens on this side. Okay. What I was supposed to say, that now we have something pretty handy to calculate deflection angles as long as we know the potential. And there is some other nice thing around here. So this equation now can have any number of solutions depending on the form of the potential and your image position. And this is how we can distinguish the different regimes of lensing. So we are doing strong lensing here in this course, which mostly happens when generally happens where this equation is going to have more than one solution, where we can form more than two images. And if you have only one image, that is weak lensing. And if you have strong lensing, but you can't resolve that, it's microlensing that we were doing this morning. This is just a brief comparison. It will be in the lecture slides of how we calculate the potential in the potential gradient and Poisson's equation in the gravity and the lensing case. And you can see the similarity here. Force and deflection angle and density and the surface density. But what I would just briefly try to stress is that the image positions here, which are this theta. So this is the source position, you can't change that. Here you have theta. These are the image positions we are interested in. And they depend on the gradient of the potential, basically depend on its first derivative. I'll skip the next slide, which is just introducing convergence, or just to explain, convergence is a handy thing where you relate your surface density to the critical density. So now your second derivative of potential becomes convergence, but that's not important in this case. What is going to be the painful bit here is the magnification. And I'll try to go through it this way. So we know from yesterday that your magnification and now is area of your image over the area of your source. And if you do this in a differential form, so here you have your image area over infinitesimal change. It's basically your magnification times your the corresponding source area. So if you have a small angle in the source plane, let's say beta, and there is d beta. If you lens it forward, you will have something much larger, theta, d theta, and the areas of these two are related by the factor mu. So your mu is theta d theta over beta d beta, and here I'm dropping the positive negative sign for the sake of simplicity. So you can also So what happens if there is no lens? If there is no lens, you remove it completely. So there is no lens, that means nothing changes. Your source looks, without lensing, is just the same source as you had before. You are looking at the galaxy, no lensing, it looks the same. Okay, this is going to be... So basically for no lensing, mu equals 1 and theta equals beta, d theta equals d beta. And now now we can use, now we can basically only consider if you now expand your theta into two, so your theta is a vector. Now it's expanded into two components. So this is the radial component and the tangential component. We are doing the cylindrical coordinates. And so does beta. So what we would like to, what basically lensing does and the magnification does, it tells you how does your beta r, beta theta, beta phi goes to, how do you do this transformation? And fair enough, we'll do some vector, just some simple matrix multiplication. So if you consider this as a two-dimensional vector, if there is no lensing, you get these two angles, you get these two components from these two components just using an identity matrix. Because what happens now is your source stays the same. So what you will observe, the radial extent of the source and the tangential extent of the source are the intrinsic ones. Yeah, the nasty thing is when we put the lens in, because then then this doesn't apply. There is some transformation happening. So your theta r will depend, if I go back, you'll start introducing dependence on your potential, because there will be a deflection angle going in both radial and tangential directions. So your alpha will also have these two components. And before I make us lost even more, think of the lensing equation where beta is now equals theta minus delta vector phi. So if you would reverse this, beta r, beta theta will again depend on your sum. If you would reverse this equation for a second, no, let's do this. So this first component is, of course, your theta r, theta phi. We are just expanding this in cylindrical coordinates, and there is now the gradient of your potential, which is going to give you the deflection angle. Why am I doing this? Yep. So we have now just expanding this. This is equal to alpha. But alpha depends on theta. And the transformation this happens there is that this part is going to, there's going to be small infinitesimal changes. So you will have theta r, theta phi. So if you do this transformation, you'll have some component. Okay, let me say I'll do this in the afternoon, because I think I'm losing everyone and myself as well. So my apologies for that. What I wanted to say is basically, we will now have a transformation matrix. A equals, if you expand that, there's a delta function. So you can think of it as, if you are on the RR axis, you have the sigma square phi over sigma square r, sigma r square. Here you have minus the cross terms. Sorry, we will actually not use this. So we have a matrix here. If there is no lensing and lensing potential is 0, this reduces to the identity matrix, which is what we would expect before, that without lensing, your beta and theta stay the same. And the magnification is going to be just an inverse of the determinant of this matrix. And that is a result that I only wanted to stress that magnification will depend now on the second derivative of the potential, and this is something we'll go back to on Friday. But I'll leave this behind, so feel free to not follow that. And I'll go back to how we actually can solve for the elliptical galaxies. And so we said that as for non-spherical galaxies, they are difficult to solve by hand, but we can use a trick from the optics, which is somewhat related to the potential we were introducing before. And probably all of you know the Fermat's principle from optics, which is often said that if you have light ray going between two paths, it takes the fastest route between these two points. So that's why if you have a bulk of glass, the light goes in here, then changes its path, then goes over here, and if you would integrate how much time it spends over this path compared to any other option you have, this would be the shortest path in terms of time, the fastest one. Except that's not correct. Because then how would you explain this? So this is a beam splitter. Maybe you know it from optics. It is a partial reflection. Even when you have non-polarized light, some part of the light goes straight, some part of the light gets reflected. But if the light was always choosing the fastest path, it would choose one of them, right? Like, these two paths are very unlikely to have the same time that the light spends going on them. I mean, this goes to a completely different point somewhere else. But somehow different photons choose different trajectories here. Some go straight, some go up. And the point is that the proper version of the Fermat's principle says the light still takes always the fastest path, but the fastest path not in general, but compared to nearby paths. So for the light going straight, a path that would go slightly differently here or slightly differently here would take definitely longer than this path. So we go through here. But there is another option which is going up here. And this is where the ray optics, simple ray optics start failing. The light is away. There is some probability of light going this way or up here. And how many photons will choose this way and this way depends a bit on how fast the paths actually are. And it's not completely esoteric, because a similar thing happens when you have a wine glass. And this is something I took from Phil Marshall. If you would take a wine glass, such as over here, and you have a point-like source in the back, it actually works a bit of like a gravitational lens. And I'll have a glass that we can pass around. And you can try it on some source. I didn't bring my lighter today, unfortunately. But basically here you see the same thing. In principle, if the light was only choosing the fastest way, you would have one image of this candle flame. But hang on, you have 4 here, you have 2 and 1 here, you have an Einstein ring over here. I don't have a drinking problem, but this is a very neat exercise. And so this basically, this is the 4 paths you would see here, the 2 paths you see here, the massive amount of paths you see over here are these stationary things. They don't have to be the global minima of your light travel path. They only have to be a local minimum or a stationary point, a saddle point, or even a maximum, but that is extremely rare and no photon would actually choose to go through that. So look at this image for a bit. Like we have 1, 2, 3, 4 images. 1, 2, 3, 4 images. 1, 2, 3, 4. 1, 2, 3, 4. And so what you can think, basically we apply this principle to gravitational lensing. The positions of these 3 images here correspond to these fastest paths for light with respect to other corresponding paths in the neighborhood, around each of these points. So what we would like to do is to do the calculation. If you have a source, here is a lens, here is an observer. What is the light travel time for a light that left the source, got lensed, and hit the observer? And do this for all the different paths that are possible, and then pick the one that are stationary points, maxima, minima, saddle points. It turns out that this calculation is not a problem. So now I'll introduce the last part of this theory class, which is the time delay function. And I'll just explain what is happening here. So you have your source, there's a lens around here. Now that lens has a mass, so it's deforming space-time. Here is an observer over here. So there are 2 things that are happening. So first one is that the light that goes around this path, let's consider this path, and the light that does something like this. How long does it take for the light to travel this path and this path? Well, there are 2 components of that. The very first one is how long is the geometrical path, right? This seems longer than this, so very likely the light So light should travel, it travels at a constant speed. So it's going to travel along this path. It will take it a bit longer than traveling along this path. It's just a geometrical thing. Longer path, light goes at a constant velocity. We are forgetting about any changes in optical index here. So longer path, longer time delay. And then this would be nice if we weren't doing general relativity, because general relativity actually has some space-time dilation. Yesterday at the very beginning we said that general relativity relates your gravitational potential to some effective optical index. So what happens is that the optical index that is seen by the light down here will be different than the one over here. If I do it very naively, I would say over here, when the light encounters the lens, it slows down proportionally to how strong is the potential here, because the optical medium got dense. Here it's less dense, far away from the lens, no change. So you have two components of this. For most of its travel time, the light would spend thousands of megaparsecs going through vacuum up to the lens, thousands of megaparsecs going through the vacuum from the lens to us. And then there is the gravitational time delay happening. There is something happening to it at the lens. And so does up here. And so all we have, the light travel time is basically a combination of this gravitational time delay, which is related to the strength of the potential, and a pure geometrical consideration, how long is from the source to the image position to the observer. So you can compare this, so you can combine these two. We're using a lot of prefactors, but basically what it boils down to in the first approximation is that there is the geometrical path depends basically on the separation between the image you see and the source, the projected separation, because these distances are pretty much fixed. So the main thing that changes here is this distance. And then there is the gravitational part that depends directly on the potential. And so how do we find maximum or a minimum of a function or a stationary point? We take a simple gradient of it, right? If I have a function and I want to find its minimum or maximum, in 1D, I just take the derivative with respect to x. And if the function is at the maximum, it's having a peak, the derivative up here is 0, it has a minimum. So at the through, the derivative is 0. And we just do it in the 2D. And I'd like you to go to the Kahoot now, because I think the question is up there. So consider the Shapiro time delay, which is the gravitational time delay. So this is the second part of this equation. Where is it going to be the longest? Is it going to be the longest for the image that is closest to the lens? The image furthest away from the lens? The image closest to the source? Or the image furthest away from the source? Oops, did I? So when we consider this function, the gravitational time delay depends to the first order on this term only. The source position is given by beta. There is no direct dependence on beta here. There will be one for the lensing equation, but let's forget about that for a second. So basically, whether the image is close to the source or not for Shapiro time delay doesn't matter. So these two options are eliminated. And then we have two options, the image closest to the lens or the image furthest away from the lens. And we know that that the time delay is the is basically proportional to minus lensing potential. So we saw before that lensing potential is going to be always negative. Minus something negative is positive. And we know that the lensing potential the magnitude of it will get the lensing potential gets more negative the closer you get to the lens. So if you take a negative sign of that, as you go closer to the lens, the lensing potential minus lensing potential and the time delay goes up. So image closest to the lens will have the largest gravitational time delay, whereas the image furthest away from the lens will have the smallest gravitational time delay. You can also take this in a limit that image that is completely away from the lens will never know there is a lens. There is no reason for it to care about the gravity at all. And the question I didn't put in the quiz, but it's somewhat related, is what would happen if you took the geometric time delay, which is now only proportional to the first term here, which is the distance between the image and the source. And then now we care about the source position, and you can easily see that if the source position is identical to the image position, this geometrical time delay gets 0, and everything else will get positive because this is coming as a square, as a second power. So for the gravitational time delay, the image closest to the source the image furthest away from the source, my apologies, will have the shortest time delay, will have the longest time. And again, you can think of it through here. If I force my ray to go through a point somewhere down here, it's going to have to take a much longer path than if it can take a much straighter route. And we'll briefly explore this on Friday morning. The last thing I wanted to say, and this is how we solve the elliptical lens. So we know that the images will be formed at stationary points of this two-dimensional function. So the only thing we have to do is to forget about the prefactors. This is the term that matters. And take a gradient and set it to 0. And if you would do this for singular isothermal sphere, I'll just explain briefly. So for the singular isothermal sphere, what happens if this is your 0, and here is your time function, the gravitational time delay is the highest closest to the lens, and then it falls off. The geometrical path delay, which is proportional to theta minus beta square, does something like this. For a source that's right behind the lens. Which is this case. And so we have minimum here, maximum here. I'm just sketching the term in the brackets here. So this term over here, if I sketch it for single isothermal sphere, I have 1, 2, and actually a third image in the center, which is not what I said before, right? Where I was saying that single isothermal sphere will have typically 1 or 2 images, but this is where you have an Einstein ring. This will be circular symmetric. There is a potential for your ray to go straight for the center of the lens. The problem with a single isothermal sphere is that's where the singularity happens. So this image is actually, this is where your ray optics approximation fails again, like it did many times yesterday. And you are left with 2 images which, through the circular symmetry, form an Einstein ring. if you offset your source a bit, so if this term, if your beta is not 0, you tilt this a bit and think of it as a Mexican hat. So this is your Mexican hat if your source is perfectly centered behind the lens. If you move away from the center of your lens, your Mexican hat gets tilted. There is still, where we go? Down, so it gets tilted. There will be a minimum down here. There is going to be a maximum where the top of the hat is, and again, this is where the singularity will happen, so forget about that. And there is going to be a saddle point, as you have the head doing this. In this direction, you'll have the minimum, so you have like one. Let me explain. If you tilt this entire thing, so in this direction, there is a minimum here. But if you would do this in a 3D, so now I'll do my head in a 3D, you'll see that there is, in the other direction, we have a saddle point. In the other direction with maximum, so this is basically a saddle point. But we still have one image over here, one image over here, which we saw before. And then if you put your source completely away, and I would almost tilt my head sideways, the only image I'll have is the one that gets caught down here in this point. Because there's no longer, the top doesn't matter, this is all going uniformly down until the single point that you have over here. And in the final few minutes, blah, blah. That's basically what I was just explaining. what I was just explaining. I would like to explain what happens in the elliptical case, which we don't have to do by hand, but it would be nice to see. So in the elliptical case, we need to split this into two components. We no longer have circular symmetry. We have to put in the ellipticity of our potential, which is just the axis ratio. So now your theta splits into theta 1, theta 2, the two components. They can be x, y, they can be cylindrical coordinates. And so this becomes your potential. And the only thing you have to do now is basically plug this expression into here and solve, and mostly numerically. But I can try to do a sketch. So this is what would happen if you are looking from the top. So this is the same function perfectly aligned. So now we have the source perfectly aligned with the lens. And what you see here, so these lines are positive contours, these are negative contours. We are in the Mexican hat situation again a bit now, if it's centered. Here is in the center of the image, there is going to be a maximum. And then there is this long circle of minimum, which is going to give you a full Einstein ring. If I put some ellipticity in and I start moving the source away from the center of symmetry, I'll have minimum here, minimum here. This is not going to be very nicely seen. There's a maximum here, and there's going to be a saddle point over here. So minimum, minimum, saddle point, maximum. Ooh, 4 stationary points. We can make 4 images. And we can move the source further away, and again, here we have minimum, minimum, stationary point, maximum, 4 images. And I can do this in a bit more visual way. So what now happens is we have, with a singular isothermal ellipsoid, we'll have 3 different regimes. If you are super far from the lens, this is the sign point, you get a single image, slightly deformed. very much weak lensing. This is the same thing with a single isothermal sphere, far from the lens, single image. Then you have this critical, then you have this outer caustic. We saw also in the single isothermal sphere, you go inside and you have two images. You have one image over here, one image down here. The same thing as with a single isothermal sphere. And then you have the inner caustic. And if you go inside of that, you'll get 4 images. So if I go just inside of this caustic, I'll have suddenly 3 images over here. These are 2 minima, saddle point, maximum. And if I go to the center, I have a super faint image over here, or no image depending on whether you have singularity, and 1, 2, 3, 4 images in a perfect symmetry. Of course, I chose some preferred axes here, which we call cusp geometry. I could do it from the sideways. I could also do it sideways. So far from the source, I get 1 image. I cross the outer caustic. I get 1 image, and a second what the hell? And a second image over here. And as I move more inwards, I start adding more images. So in this particular case, you will have a solution with 3 images. If you are in between this regime, you go inside the diamond caustic. 2 of these, and 1 of these images will start splitting into 2 until you get again to the center of the symmetry and you have a nice cross. And this is the final slide that I'll show today. This is the RxJ1131, and I was promising we'll try to understand it throughout this week. Now you have the 3 images over here. And now we have 3 approximate geometry for where your source might be and how the image configuration will look like. And I think you can start seeing for yourself where is the source going to be positioned with respect to the lens. We have 1 image, 2 images sort of symmetrically off from it, other image on the other side. So this doesn't look like this. They are not completely symmetric, they are not in a cross combination, so the red option is ruled out. But the green option over here works pretty well. And I'll show you tomorrow a high-level reconstruction of this galaxy, and you will see that the quasar is indeed located in this caustic, right here in this position. This afternoon you'll have a chance to try this on more systems. I'll provide you with some choice lenses to look at. And this is where I will wrap for today. Thank you very much. Final thing, starting from tomorrow, we leave the theory behind and we move to the actual science, the ongoing surveys, how to find gravitational lenses, how to learn something about the background sources, and how to test cosmology and dark matter with them. Thank you very much.